we're going to develop derivatives of the inverse trig functions, and we're going to start by considering an equation x is equal to the sine of y. Now, this is true if and only if y is equal to the inverse sine of x, of course. If we take what's on the left-hand side and differentiate with respect to x, then on the left side of y equals sine of y, we get 1. And on the right-hand side, if we use implicit differentiation, then we get the derivative of the sine, so cosine of y, times the derivative of the inside function, so times y prime. Which means that if we divide both sides by the cosine of y, we get y prime is equal to 1 over the cosine of y. While true, we can make this into a more useful form. If we consider a right triangle based on the equation x is equal to the sine of y, then that means that we can identify in our right triangle an angle y, and the sine should be x over 1. The third leg of this triangle by the Pythagorean theorem is going to be 1 minus x squared. As it turns out, the cosine of y for this triangle is the square root of 1 minus x squared. This means that we can replace the denominator cosine of y using an expression in terms of x. So y prime equals 1 over 1 minus x squared. You wouldn't have to write this down, but I will note for you that notice that because of where x is in the square root, that its value has to be between -1 and 1. And I wrote inclusive, but it can't be inclusive because the denominator cannot be 0. Now, what we've just developed is a differentiation rule for the inverse sine function. Since y is the inverse sine of x, we now have y prime, and we can write down that the derivative with respect to x of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. Using a similar process, we can say that the derivative with respect to x of the inverse cosine of x is equal to the negative of 1 over the square root of 1 minus x squared. The negative would come about because at some point we would be differentiating the cosine function, and the derivative of the cosine is the negative sine. Here's another way to look at it. The inverse sine of x plus the inverse cosine of x is equal to pi over 2. Now, I know that's quite an assertion. Let's explore this just a little bit. Inverse sine of x. So I'm saying there exists an angle alpha whose sine is x. So the sine of alpha is x. Alpha is the angle whose sine is x. And then there's another angle, let's say beta, whose cosine is x. Right? So the cosine of beta is x. Beta is the angle whose cosine is x. Now we can put this into the context of, oh look, a right triangle. I am going to make angles here alpha and beta. Let's say the sine of alpha is equal to x. I mean, we've already said it. Let's draw it. X for the vertical side, 1 for the hypotenuse. You see this angle beta? Its cosine happens to be x over 1, because cosine is the adjacent over hypotenuse. And we can see, because this is a right triangle with acute angles alpha and beta, it must be the case that alpha plus beta is equal to pi over 2. Therefore, the inverse sine of x and the inverse cosine of x are pi over 2. Well, when you add them together anyway. So it follows that the inverse sine of x is equal to pi over 2 minus the inverse cosine of x. Now differentiating both sides gives me on the left-hand side 1 over the square root of 1 minus x squared. On the right-hand side, differentiating pi over 2 gives me 0. And differentiating the inverse, well, hey, I'll just write it as negative derivative with respect to x of the inverse cosine of x. And I hope that I've just convinced you that the second differentiation formula that we wrote, the one for the inverse cosine function, is true. Now let's get rid of this because I'm going to need that space in just a little bit. Okay, back to this process by which we develop the derivative of the inverse sine function. If we did that repeatedly with the various trig functions, then we would end up with the following. And I encourage you to develop these on your own. the derivative with respect to x of the inverse tangent of x is equal to 1 over x squared minus 1. Notice there's no square root, and that's because the derivative of the inverse tangent function, excuse me, that's because the derivative of the tangent function is the secant squared. The derivative with respect to x of the cosecant inverse, or the inverse cosecant of x, is equal to negative 1 over x times the square root of x squared minus 1. The derivative with respect to x of the secant inverse, the inverse secant of x, excuse me, is equal to 1 over x times the square root of x squared minus 1. So we're seeing a similar relationship between what we see for the inverse sine function's derivative and the inverse cosine function's derivative, and that's being mirrored with the inverse secant and the inverse cosecant. That is, one derivative is negative and one is not. Continuing on, last one, the derivative with respect to x of the inverse cotangent of x is, well, looking at the tangent function, can you guess? It's going to be negative 1 over x squared minus 1. Well, folks, once we have differentiation rules, we have integration rules. So, because the derivative of the inverse sine of x is 1 over the square root of 1 minus x squared, the integral of 1 over the square root of 1 minus x squared dx must equal the inverse sine of x plus our constant. Let's skip the cosine for now. Reversing the derivative of the inverse tangent gives us that the integral of 1 over x squared, that should be a plus 1. It's a plus 1, folks. Everybody look, this is a plus 1 right here in the denominator. For the inverse cotangent, it is a plus 1. Oh my gosh. Okay, the integral of 1 over x squared plus 1 dx is equal to the inverse tangent of x plus c. And let's skip the cosecant. Reversing the differentiation rule for the inverse secant function, we get that the derivative of 1 over x times the square root of x squared minus 1 dx is equal to the inverse secant of x plus c. Now, what about the inverse cosine function? Well, the derivative of the sine and the derivative of the cosine only differ by a minus. So if I had, for instance, the integral of negative 1 over 1 minus x squared dx, I would just call the answer negative inverse sine of x plus c. It's not substantially different to consider the cosine function. So what we've actually done, when I say we, I don't mean I mean the math community, they took a vote. I don't know what happened. But it has been determined that we're only really going to answer these types of integrals in terms of the inverse sine, the inverse tangent, or the inverse secant. And so, you, as a student who's going to do work on this stuff, if you see an integral that it looks like 1 over square root of 1 minus x squared, you don't have to consider writing an answer of inverse cosine. You're only going to write down an inverse sine, okay? Likewise, inverse tangent, inverse secant. You won't be answering integrals with inverse cosine of x, the inverse cosecant of x, or the inverse cotangent of x. I would like to point out that we do have restrictions on the values of x. And as we pointed out earlier, for the inverse sine and inverse cosine, their derivatives are 1 over the square root of 1 minus x squared, and so x has to be in magnitude less than 1. The way I think of that is x can't get too big. Otherwise, you have a negative inside your square root. For the inverse tangent and the inverse cotangent, we have x squared plus 1 in a denominator. Those are unrestricted. X can be any real number. So there we go. X can be any real number for inverse cotangent, inverse tangent. For the inverse cosecant, we see that we have a square root in which x squared is the first term, right? We have x squared minus 1. that means that x can't be too close to 1, right? X not less than. X has to be in magnitude greater than 1. Because if I'm going to square it and then subtract 1, I need a real number, or I need a positive number in there. So I think of the sine function as, or the inverse sine function, x can't be too big. Magnitude or absolute value of x is less than 1. For the inverse cosecant or the inverse secant, x can't be too small. Absolute value of x has to be greater than 1.